In this video, we're going to talk about how to name alkenes and also some factors that influence their stability. So when we're naming alkenes, we follow a lot of the same rules that we use for naming alkanes. There are just a couple modifications that we have to keep in mind. So the first of those is that when we identify the parent chain must include the carbon-carbon double bond. So even if I could make a longer chain that didn't include the carbon-carbon double bond, it would not be the parent. Another big difference is that when we're assigning, or when we're deciding how to number the chain, the carbon-carbon double bond has to have the lowest number possible. So it doesn't matter what's going on with the other substituents, the carbon-carbon double bond must have the lowest number. And then we need to say where the carbon-carbon double bond is, and we can either do it just before the parent name or just before the -ene suffix. So if we look at a couple examples, when we're naming alkenes, the end of the parent chain gets changed from an ane, right? So in an alkane, this would be pentane. In an alkene, we change the suffix to ene. So a 5-carbon alkene would be pentene. Right? Now, when we're determining the parent chain, you can see in this case, our parent chain would be octane, because the longest chain we can make is 8. In this case, I can make a chain of 8, but it doesn't contain the carbon-carbon double bond. So in this case, we would have to name it as heptene, 1, 2, 3, 4, 5, 6, 7. All right, now we identify and name the other substituents just like we would before. When we're assigning the numbering, the alkene, the carbon-carbon double bond, it gets the highest priority. And so it determines which side we're going to number from. So even though I have a 2-methyl, and then I could get more substituents with lower numbers if I started numbering from this side, because the alkene, the double bond, would have higher numbers, this is incorrect. And so the correct numbering gives the carbon-carbon double bond the lowest possible numbers. All right, and then finally, we have to say where the carbon-carbon double bond is, and so we can do that in one of two ways. So we can either put the 2 in front of the parent chain, or we can sort of have the prefix that tells me how many carbons there are, then the 2, and then the ene. And then another important note, if we have E or Z isomers, then we have to indicate that in the name. And so the E or Z label goes at the front of the name. So let's look at a couple examples. All right, so in this case, first thing we want to do is figure out what our parent chain is. And the longest chain I can make is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But that doesn't include the carbon-carbon double bond. So the longest chain with the carbon-carbon double bond would be 1, 2, 3, 4, then we can go 5, 6, 7, 8, or 1, 2, 3, 4, 5, 6, 7, 8, 9. And so I think this then is going to be the longest chain that we can make with 9 carbons. All right, and then the other substituents. So I have a substituent here. This is a 4-carbon substituent, so this would be a butyl group because they're all in a straight line. It's just simply butyl. Then I have an isopropyl. And then I have a methyl. When I'm numbering my parent chain, the carbon-carbon double bond has to have the lowest number. So I'm going to start numbering from this end. And so I have 1, 2, 3, 4, 5, 6, 7, 8, 9. So when I go to list the substituents, the butyl is going to be first alphabetically. So I have 4 butyl. Then the isopropyl would be next. So I have 5 isopropyl. I have 7 methyl. And then when I give the number for the carbon-carbon double bond, I usually like to put it in front of the parent chain. And so I would call this 2 nonene. All right, and then the other thing we need to check and see if we have E and Z isomerism. And in this case, I think we do. And so in this case, the highest priority groups are here. Let's go ahead and circle that. So we have, right, I have here and here, right, compared to the H's. So the higher priority groups are across from each other on the double bond. And so then this is going to be E, 4-butyl, 5-isopropyl, 7-methyl, 2-nonene. Okay, one more example. So first thing we want to do is find the longest chain that includes our alkene. And so I think that looks like it's going to be 1, 2, 3, 4, 5, 6, 7. So I have heptene, and I need to go ahead and name my substituents. So, and in fact, let's do the numbering first. So I'd start numbering here: 1, 2, 3, 4, 5, 6, 7. And then I have, right, this is going to be 2-methyl. This is going to be 4-ethyl. And this is going to be 6-bromo. And so the bromo comes first. So we have 6-bromo. Next alphabetically would be the ethyl. So I have 4-ethyl, 2-methyl, and then it would be 2. We said there were 7, so it's heptene. All right, and then we want to check if we have E and Z isomers, but both groups coming off this carbon number 2 are methyls, and so we don't have E and Z isomers in this case, and so this would be the complete name. All right, the last thing I want to talk about in this video are some factors that influence the stability of alkenes. So in this case, I have 1, 2, 3, 4. I have butene, and so I have trans-2-butene and cis-2-butene. And in general, alkenes prefer to be in the trans configuration, or where the bulky groups are across from each other. And so in this case, the trans-2-butene is going to be more stable than the cis-2-butene. And so we want to keep the bulky groups on opposite sides of the double bond when we can. All right, another thing that influences the stability of alkenes is how substituted they are. So how many carbons are coming off of the double bonds, right? So in this case, right, I've got hydrogen, 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 right? So there's only one carbon on this alkene, and so this would be monosubstituted. And so as far as alkenes go, that's not particularly stable, right? In this case, I have 2 carbons coming off the double bond. This would be disubstituted. I have trisubstituted and tetrasubstituted, right? In general, the more carbons I can have coming off the double bond, the more stable they are. So a tetrasubstituted alkene would be much more stable than a monosubstituted alkene. All right, and then one other note on stabilities. Cyclic alkenes are almost always cis, right? To make these trans, right, there just aren't enough carbon atoms to sort of fold around that. And so the only time we see trans is when we have rings containing 8 or more carbons. So the vast majority of the time, the cyclic compounds are going to be in the cis configuration. And so we don't need to specify whether it's cis or trans, because only the cis is possible. All right, finally, one example. If we wanted to rank these constitutional isomers in terms of stability, the first thing we would look for is how substituted they are. So this one and the third one are both disubstituted, while as the one in the middle is trisubstituted. So I think the one in the middle is going to be the most stable. And then when I compare the first one and the third one, the only difference between these two is we have the trans isomer and the cis isomer, and so we can get these bulky groups away from each other. So the trans is preferred, so then this one is going to be the least stable, right? And then this one, we'll call that the middle stability, at least for these 3 compounds.